Okay, welcome everyone. This is Calculus 1, Lecture 3, the laws and properties of limits. Okay, so first off, we're going to talk about limit laws. These are laws that are going to allow us to compute limits by simplifying complex expressions into simpler pieces and then evaluating those simpler limits one at a time. So to get started, let's suppose that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. We will come across limits that don't exist, and that might make things a little bit more complicated. But for now, we're going to assume these exist and that c is a constant. Then let's go ahead and look at our first limit law. Number 1 says the limit of a sum is the sum of limits. Okay, so the limit here is the overarching operation. It's applying to this sum between f of x and g of x that's already been computed within these brackets. We can go ahead and we can actually break that apart. It's almost as if we're distributing the limit to each function individually and then computing that first before adding them together. Okay, so this limit law allows us to do that. The same thing is true for the limit of a difference. This is going to be rewritten as the difference of limits. Okay, so you've got that overarching limit operation outside, you've got the difference inside, and again, we can apply that limit to each function individually. The next one says the limit of a multiple is the multiple of a limit. Same idea. So if we've got, within our brackets, we've got some constant multiplying by our function, we can essentially just pull that constant out. We can remove that from here, and it has no bearing on the computation of the limit that we're going to do first. So we're going to calculate the limit of f of x first. It's dependent on x approaching a, not c, so we can just compute that later. We can do that at the end. The limit of a product is the product of limits. Now this is a really useful rule, especially as we're going to see later on in calculus. We don't often get product rules like this. This is really convenient. So we're allowed to even break apart products. So the limit of a product of f of x and g of x is the product of their limits. Naturally, the same thing is going to hold for division. The limit of a quotient is the quotient of limits just as long as you're not dividing by 0. Okay, so long as you're not dividing by 0, we're allowed to go ahead and do this. So we have a limit of a fraction of two functions. That limit will go into the numerator and the denominator as long as this is not going to give us a 0 in the denominator. Okay? Our next rule, number 6, the limit of a power is the power of a limit. So if we have the limit as x approaches a of f of x raised to the nth power, we can go ahead and we can throw that limit inside the power. Okay, so we can compute this first, the limit as x approaches a of f of x, and then raise it to the nth power at the end. And since roots are really just powers, the same way division is really just a different form of multiplication. It's multiplication by a reciprocal, right? Roots the same way, so if we can apply this power rule, we can also apply a similar root rule. Okay, so the limit of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. It's the same deal. All right, now let's look at some examples. So suppose they predefined the limit as x approaches 6 of f of x to be 4, the limit as x approaches 6 of g of x to be 9. Then we can go ahead and we can try to compute each one of these limits using the laws that we've just seen, laws 1 through 7. So you can go ahead and you can take a second to pause the video and try these out on your own. Okay, so first off, we have a, which is the limit as x approaches 6 of 2 times f of x times g of x, where the limit as x approaches 6 of f of x is equal to 4. The limit as x approaches 6 of g of x is given as 9. Okay, so first of all, we identify that we have a constant multiple in here that we can bring out. So this 2 will come out front according to rule number 3. Now we're left with the limit of a product. So although we have the definitions or the values for each individual limit, we don't know what the limit of the product of these functions comes out to. So we can go ahead, we can break that apart using rule number 4, which is the product rule, and now we can substitute individually for each limit, okay, and evaluate what this comes out to. So the limit is x approaches 6 of f of x is equal to 4. The limit as x approaches 6 of g of x is equal to 9. We multiply those out and we get 72. Okay. For example B, now we've got the limit as x approaches 6 of the sum of f of x and 1/3 times g of x. So first of all, let's use rule number 1. Let's break this sum apart. Now we've got the limit as x approaches 6 of f of x plus the limit as x approaches 6 of 1/3 gx. Now, in that second one, we've got a constant multiple to bring out. So that 1/3 can come out front. And now we can substitute in individually for each limit. So we're going to get 4 plus 1/3 times 9, and that's going to come out to 7. For example C, now we've got the limit as x approaches 6 of the square root of g of x minus f of x. So let's use that root rule, rule number 6, which is going to allow us to place this limit inside the radical. So now this is the limit of this difference, and then the square root of all of that. So now the square root is the outermost or the last operation. Next, we can use rule number 2 to break apart the difference and apply the limit to each of g of x and f of x. And now we're ready to substitute. So the limit as x approaches 6 of g of x is again 9. The second one is going to be 4. The square root of 9 minus 4 is just going to come out to the square root of 5. Example D. The limit as x approaches 6 of the product of x plus 1 times f of x. Okay, so the only one that we really have to substitute in here for is the limit as x approaches 6 of f of x. So let's go ahead. We'll use rule number 4. We'll break apart this product to begin with. Now, for the first one, we can just use direct substitution to simplify this. So we can just put in that 6 for the x. We're going to get 6 plus 1. For the second one, we can substitute using our definition, and this becomes 4. So we're going to get 7 times 4, which is just 28. All right, so let's take a look at the next few examples then. Now we're just finding limits, but let's see if we can use our limit rules to sort of help here, right? So E says the limit as x approaches 3 of the cube root of 2x squared minus 10. Now we have the root law, which is going to allow us to place this limit inside this cube root. Okay, so this is really just the cube root of the limit as x approaches 3 of 2x squared minus 10. And now from here where we have our function of x, we can go ahead and we can use direct substitution and simplify this. This is going to come out to the cube root of 2 times 3 squared minus 10, which simplifies all of it to the cube root of 8, which is just 2. Okay. Example F. Now we've got the limit as x approaches negative 5 of the quotient of x squared plus 25 and x plus 5. So again, the quotient rule is going to allow us to make this into the quotient of two limits. So limit of the numerator divided by the limit of the denominator. And again, now you've got the limit of a function of f of x, limit of a function of fx. I mean, this was a function of f of x as well, but these are simple functions where we can just think of this as direct substitution. And in the numerator, we're going to get 25 plus 25. In the denominator, we're going to get negative 5 plus 5. So although we got 50 in the numerator, we're actually going to get 0 in the denominator, and this is undefined. Therefore, this limit does not exist. Okay, so the limit will not always come out nicely. This was one of our first examples. All right, next we've got transcendental functions. So these are our trigonometric functions, logarithmic, exponential. Okay, let's see how these work with limits. So let C be a real number in the domain of the given transcendental function. Okay, and we've got our rules for transcendental functions here. So we've got these 8 rules. So number 1 just says the limit as x approaches c of sine of x is going to be the sine of c. And the same thing is true for every single one of these transcendental functions. So you've got all of your trig functions, you've got your reciprocal trig functions. In all cases, you're just doing direct substitution. So whatever that c value is, you're going to evaluate that inside as the argument of your trig function. The same thing is true for an exponential function. Just replace that exponent with c. And same thing for the argument of a logarithm. Just go ahead and replace that with c. So all of these rules are just telling us that we're allowed to do direct substitution in the way that's most intuitive to us. Okay, so let's go ahead and apply them. Example H, limit as x approaches 0 of sine squared x. So considering that, we had our power rule from before, we have now our transcendental rule. Essentially, all this means is I can just go ahead and plug in 0 into that x. Okay, so we're seeing this as a power. We're considering this now the power of the limit of sine of x. And then we're going to go ahead and apply rule number 1 for our transcendental functions. We're just going to directly substitute 0 in for x. So sine of 0 squared is going to be 0. Okay, example I, limit as x approaches negative 1 of x times e to the x. So this is the limit of a product, which is the product of their limits. The limit as x approaches negative 1 of x times the limit as x approaches negative 1 of e to the x. Go ahead and use direct substitution on both of them. And we're going to get negative 1 times e to the negative 1, which is just going to come out to negative 1 over e. Example J, the limit as x approaches e of ln of x cubed. Okay. Now the first step here is going to be applying the power rule of logarithms. So if you recall, if I have something like log base b of x to the a, and this a is inside the log, that a can actually come up front, and I'll get a log base b of x. So that's exactly what we're going to do here. That 3 is just going to come out front as a multiple. And then once I have that multiple there, I can actually just take it entirely out of the limit. So I have 3 times the limit as x approaches e of ln of x. We use direct substitution. Ln and e are inverse functions. They just come out to 1. 3 times 1 is going to be 3. Okay, so those are just some quick examples with transcendental functions. And we're seeing that limit laws are allowing us to do some really convenient simplification on all of these functions. Then we've got some special limits. Okay, so what are these special limits? So the first one is the limit as u approaches 0, and I'm just using u here as a placeholder variable, We'll see why in a minute later on, but you could have used any letter here, including x. But the limit as u approaches 0 of sine of u over u is equal to 1. And even though this seems like something that would be undefined, it seems like something that would cause a problem, but it's actually found that this reduces nicely to 1. And similarly, you have the limit as u approaches 0 of 1 minus cosine of u over u. This comes out to 0. Okay, and I want to make a note here. So for number 1 here, if you're given the reciprocal of this, if you come across the limit as u approaches 0 of u over sine of u, well, we can just do some algebraic rearrangement and make use of number 1 and still simplify this, even though it's in the reciprocal format. So this is just the same thing as 1 over sine of u over u. Apply your quotient rule for limits. Take the limit of the top, that's just going to be 1. And then take the limit of the bottom, that's going to be this new special limit rule that we just learned. So this is just going to come out to 1 over 1, which is still 1. Okay? And you could do something similar if you had come across the reciprocal of number 2. So let's look at example K. The limit as x approaches 0 of tan x divided by x. We can split this apart as a quotient or a product, however you like. I've written it here as a product. We're going to apply this substitution for tangent x. This is really just sine x over cosine x. Okay. Now you're seeing the sine x, you're seeing that 1 over x component there. We can rearrange this to now fit our form here. So we get the limit as x approaches 0 of sine x over x times 1 over cosine x. Go ahead and apply your product rule. This is going to become 1. This is going to become 1 over cosine of 0, which is also 1. Okay. Example L. The limit as h approaches 0 of pi times sine of h over 2h. So this might seem a little strange at first, but if we just break this apart, we can just think of pi over 2 as a multiple of sine h over h. And now we can use our multiple rule, bring this out of the limit. You have pi over 2 times the limit as h approaches 0 of sine of h over h. Go ahead and use that special limit rule. That reduces to 1. Pi over 2 times 1 is just pi over 2. Okay, and then we've got example M. The limit as x approaches 0 of sine of x over sine of 2x. Now with this one, we have to be a little bit clever about how we can go about doing this and making use of our special limit law. Okay, so we break this apart as a product first. Sine of x over 1 times 1 over sine of 2x. Now we can multiply by some really convenient forms of 1. Okay, so remember, we're always just multiplying by 1. It has to be the same thing in the numerator, same thing in the denominator. So I'm going to multiply that first part by x over x. I'm going to multiply the second one by 2 over 2. And let's see what that's going to give us. So this x in the denominator is going to come over here. That gives us sine of x over x for our first limit, which we already know how to reduce to 1. I'm going to take this x from here and this 2 from here and put them together to get 2x over sine 2x. Now remember, when we had u over sine of u, the limit as u approaches 0 of this is still going to be 1. And that's going to be the same rule we're going to use here. Okay? So although this is x approaches 0, that it still means that, right, 2 times x is going to go to 0. So it doesn't matter if this is x or 2x. You can just think of this whole thing as a u. And that's what's happening here. And then we just have that leftover 1/2 at the end. So this entire limit comes out to 1/2. Okay, so this has been Limit Laws. If you found this lecture helpful, please give it a like and subscribe to the channel so you don't miss the next one. Thank you for watching.